I'm presenting here three proofs that root 2 is irrational. We're going to let p, q, r, s and t be integers, and in the left-hand column I follow the proof which is most usually given. We suppose that root 2 equals p upon q, where the greatest common divisor of p and q equals 1. So root 2 equals p upon q implies that root 2q equals p. Squaring both sides, we have 2q squared equals p squared, which shows that p is even. So p equals 2r. So that 2q squared equals p squared implies that 2q squared equals 2r all squared, which is 4r squared. If I now divide both sides by 2, I find that q squared equals 2r squared, so that q is even. And this contradicts the assumption that the greatest common divisor of p and q is 1. Now, when we come to the conclusion that p is even, we could go another way. We could observe that this means that q is odd, since their greatest common divisor is 1. So p will equal 2s and q will be 2t plus 1. So if we say that 2q squared equals p squared, that means that 2 lots of 2t plus 1 all squared equals 2r all squared. So that 2 lots of 2t plus 1 all squared equals 4r squared. And if we divide both sides by 2, we find that 4t squared plus 4t plus 1 equals 2r squared. And then by factoring out the 2 there, we can show that this implies that an odd integer is equal to an even one, and which is absurd, and it's implied by the statement that root 2 is rational, so root 2 must be irrational. The third proof is a proof by descent. If root 2 is rational, then root 2 equals p upon q, where this time the greatest common divisor may not necessarily be 1. But if root 2 equals p upon q, there is a set of numbers, s1, s2, s3, such that for any one of them, sn perhaps, multiplied by root 2 is an integer. This is like saying that there is a set of numbers which, when you multiply them by 400 over 300, you get an integer. And in this case, any member of a 3 times table will do, but there must be a smallest integer which does it, and in that case it is 3. So we let s be the smallest integer which, when multiplied by root 2, gives an integer. Now consider the number root 2 minus 1. 1 is less than root 2, which is less than 2. And so subtracting 1 from each side, we find that 0 is less than root 2 minus 1, which is less than 1. So if root 2 minus 1 is less than 1, s times root 2 minus 1 is less than s. But s times root 2 minus 1 equals s root 2 minus s, which is an integer less than s. If we multiply this by root 2, we get s root 2 times root 2 minus 1, which is 2s minus s root 2, integer minus integer equals integer. So the supposition that root 2 is rational leads to the conclusion that there is no smallest integer s such that s root 2 is an integer, which is absurd.